In this video, we are going to discuss about eigenvectors and eigenvalues. Now, already in my previous video, I've spoken about it, what eigenvectors and eigenvalues can actually do. See, at the end of the day, we have to find the best principal component line, which will be able to capture maximum variance. And in order to find this, we will be using this eigenvectors and eigenvalues, because in short, whichever eigenvector, like if suppose let's consider that we have some data points. Let's say I have some data points over here, and this data points, let's say I want to find out the best principal component line in such a way that once we make sure we project this right in this particular line, we should be able to capture the maximum variance. Now, what is so amazing about this eigenvectors and eigenvalues, and we'll also be talking about linear transformation, okay? And we also say it as eigen decomposition of covariance matrix. That basically means for this particular matrix, we will try to find out the eigenvectors and eigenvalues, okay? Now the most important thing about these vectors is that, suppose let's say I have a specific matrix, okay? I can have any specific matrix. On this matrix, or if I have a vector, let's say the vector is v, okay, and this vector will have a different coordinates. Let's say if this vector, on this particular vector, let's say if I apply some linear transformation, okay, what does this linear transformation basically mean? I'll give you an example. That basically means on this particular vector, let's say if I apply a linear transformation with this specific matrix, then I will be getting one lambda value, and this lambda is nothing but my eigenvalue multiplied by the same vector. So here you can see that this basically means that, suppose I have a vector with this particular dot. On top of this, if I apply linear transformation, what does linear transformation basically mean? Let's say I have my coordinate system, and right now it is in this grid manner. Okay, let's say this is entirely all my data is in this grid manner, right? When I say linear transformation, this entire data can be moved, or this entire plane can be moved in different direction. Okay, I'll just show you one example directly. So always understand, in order to compute the eigenvalues and vectors, so what we do is that, let's say if A is my matrix, okay, on top of it, if I apply this matrix on the top of this specific vector, like if I apply the linear transformation on top of this specific vector, then I will be getting lambda, which is my eigenvalue, along with that same vector. So this is the equation that I will specifically be using in order to find out eigenvalues and eigenvectors, okay? And from this equation, whichever eigenvector has the biggest magnitude or has the maximum magnitude, because for a space, for a matrix, I can definitely have multiple vectors, okay? So from this, whichever has the maximum magnitude, that will be used as a plane or principal component, because it is practically proved through maths. Again, I'm not going to go towards that particular proof, but this principal component will be able to capture maximum variance, okay? So let me go ahead and show you one example, okay? So here I will just show you one example. So this is a linear transformation. Let's say I have one vector over here, okay? I have one vector. So this vector is nothing but 1, 1, right? So here I hope everybody is able to see this, okay? 1, 1. So this is my vector. Now on this particular vector, if I apply a linear transformation with this matrix, okay, with this matrix, now what will happen, you see, because once we do the linear transformation, this particular line will now get changed and it will display something like this. See, after I apply this transformation, my new points that I'm going to get is something like 4, 4, 2, right? Now 4, 2 is nothing but, here you can see the lambda value will be 4, 2, because 1, 1, 0, 1, 0, 1.01, 1.0 is my vector, right? So here also you'll be able to see I can multiply lambda multiplied by this particular number. So here you can see 4, 2. That basically means, for a vector, if I apply a linear transformation with this particular matrix, I'm going to get a lambda value with 4 and 2 as its lambda, as its eigenvalue. Now, let me just show you the eigenvectors also. Let's say here I've checked on eigenvectors, and let me also show the snap grid. Okay, so here you will be able to see what is basically happening. This line that you see, right, this is basically my vector. Okay, now here you can see for this particular point, when I apply this transformation, the vector is in another direction and this is in another direction, right? Now let's say my initial point was somewhere here. Let's say my initial point was somewhere here, and if I probably apply the same operation, now it is minus 1 0, right? Then what will happen is that you can see the new transformation, right? I'm actually getting minus 2 comma 2, and here you can see this is in the direction of the vector. So what I can do is that I can project this particular point into this plane, right? So here this will be my longest vector with this longest magnitude. Okay, just for an example I'm considering like that. If I keep on doing another points, right? If I keep on doing, let's say I'm putting it over here, right? And if I go back here, you'll be able to see this was my initial vector. Now after applying linear transformation, it has gone outside the plane. Similarly, I can, and this time vector did not match. Suppose if I have this point over here, and if I try to apply it here, you can see again this will get transformed to different values. So your lambda value will keep on getting changed based on the different vectors. Okay. So from this, we can definitely see that what is happening is that from this specific equation, we will be able to get the eigenvectors, and this eigenvector which has the maximum magnitude. When I say maximum magnitude, that basically means the max eigenvalues that will be selected as the best principal component line. Okay, in this particular case, it is PC1 because it captures maximum variance. Okay, so at the end of the day, you'll be able to see with the help of this eigenvectors and eigenvalues, you'll be able to see this. Okay, and the same thing is happening. Now let's go ahead and understand the steps to calculate eigenvalues. Steps to calculate eigenvalues and eigenvectors. Value and eigenvector, because as I said that you require a matrix, right? In this specific case, we have to calculate the covariance of the features, right? Now let's say if your features were x comma y, your independent feature, and this is your z as your output feature. So for this, I want to extract another feature which can be x dash. So what I will do is that I will try to find out the covariance of x comma y. So let me write down the equation of covariance of x comma y. So here you can see that I will be able to write summation of I is equal to 1 to n x of I minus x bar multiplied by y of I minus y bar divided by n minus 1. Okay. Now here you can definitely see that if I really want to find out the covariance of x comma y, usually we get 2 cross 2 matrix. Okay. Now this specific matrix looks something like this. Okay, let's say I'm just going to divide like this. So this will be a 2 cross 2 matrix. This will be x, this will be y, this will be x, this will be y. So if I try to find out the covariance of x comma x, then what it will become? So if I try to find out the covariance of x comma x, here you will be able to see I can also write this as variance of x. Why? Because x comma x basically means x of I minus x bar, right? So x of I minus x bar, it will be nothing but x of I minus x bar whole square, which is nothing but variance of x, right? So here you will be able to see that I will write variance of x. Here this will be covariance of x comma y. Here it will be covariance of y comma x, and here it will be variance of y. Okay, because covariance of y comma y is nothing but variance of y, right? Now this is the first step. We have to compute this specific matrix, and this is for a 2 cross 2 matrix. If I have 3 independent feature x, y, z, then I have to probably create 3 cross 3 matrix, right? I have to basically create like this 3 cross 3 matrix. Now here you will be able to see that I will be creating this kind of lines, and here will be one, here will be another, right? Now again here all in the diagonal element, it will be the variance of x, variance of y, variance of z, and remaining all you will be able to see this. And one more thing, that covariance of x comma y is equal to covariance of y comma x. This both will be equal, right? Now what we are going to do in order to find out the eigenvalues, we will take up this covariance matrix. This, let's consider it is A, and we will try to take a vector v, and this A will be taken, which will be my covariance matrix, and I will try to apply a transformation of the vector, and finally we will be getting lambda over here, and this vector will be given back. Now since I have two features over here, f1 and f2, let's say, then I will be getting two lambda 1 values, right? Lambda 1 and lambda 2. Lambda 1 will basically be giving my principal component line 1 magnitude, and whereas my lambda 2 will be giving me the principal component 2 magnitude, right? So this will be PC1, right? So like this, when you have three features, you are going to get all lambda 1, lambda 2, lambda 3, which will specifically talk about the eigenvalues. So just by using this equation, at the end of the day, you will be getting an eigenvector, and that eigenvector will be giving you 2 or 3 based on the number of features that you have, that many lambda values. Let's say if it is giving lambda 1 and lambda 2, that basically means you have 2 eigenvalues, and whichever eigenvalue is the highest over here, that will be, and it will already give that in that specific value, in like the lambda 1 will be the highest and lambda 2 will be the highest. So this way you'll be able to get this lambda 1 and lambda 2, which are specifically the eigenvalues, and then this can be considered as PC1 and this can be considered as PC2. So guys, just to revise all the steps now, what we are going to do is that let's consider the first step over here. So I'm going to write it down. The first step that again we are going to do, let's say that I have my data points over here. So let's say this is my x and y, and let's say I want to probably first of all convert this into 2D from 2D to 1D. Then the first step that I am actually going to do is basically standardize this data. Now once I standardize this data, what will happen is that all these data points that you will be seeing, it will be zero centered, you know. So here you will be able to see all the data points like this. Okay, let's say these are my data points that I've got zero centered. After this, the second step is that we go ahead and find out the covariance matrix of this x and y. Okay, let's say this is my x and y. So we basically find out the covariance matrix, and again in the case of two independent features, I'll be getting a 2 cross 2 matrix, right? So this will basically be my 2 cross 2 matrix with respect to x and y, x and y. Here I'm going to get the variance of x, and here I'm basically going to get covariance of x comma y, and here I'll be getting covariance of y comma x, and finally I'll be getting variance of y, right? Now after I get this covariance matrix, all I have to do is that find out eigen vectors and values. And how do I find it out? By just applying, let's say this is my matrix A. So this A, when we apply a transformation on vector V, I'm going to get this eigenvalue of V, right? Now since this is a 2 cross 2 matrix, here I'm going to get lambda 1 and lambda 2. Okay, so these two values are my eigenvalues. Okay, and this lambda 1 will basically be indicating me by PC1, that is principal component 1 line, and this will be my PC2 line. So in short, after this particular points, what we are going to do is that let's say that we will be creating two different line. One line may be this, one line may be this, or let me just draw it in different color. So let's say this may be my PC1. Okay, so this may be my PC1 and this may be my PC2. Okay, but as we know that the first lambda 1 value which I'm getting, which is nothing but the magnitude of the eigenvector, here it will capture the maximum variance. So this variance that is getting captured will be maximum. So we go ahead and select this. Now let's say if I want to convert from a 3 dimension to 1 dimension, then what will happen? I will get 3 lambda values, that is 3 eigenvalues. Now what I can do, I can combine this to lambda 1 and lambda 2 and probably take, okay, or since I have already explained you, this lambda 1 is nothing but PC1, this is PC2, and this is PC3, right? So I can combine PC1 and PC2 and convert this 2 dimension into 1D, and then this can also be taken as another 1D. So when I combine this two, right, it becomes a 2D, right? So if I probably want to convert from 3D to 2D, I'll be going in this way. So let's say if I want to convert from 3D to 1D, so once I find out my eigenvalue and vectors, I'll be getting lambda 1, lambda 2, lambda 3. I have to combine all these three and probably get one dimension in this case. Similarly, in the case of 2D to 1D, so let's say if I want to convert from 2D to 1D, here I'll be getting lambda 1 and lambda 2. This is nothing but my PC1. This is nothing but my PC2. So we can combine this two both and we can get a one dimension point, right? When I say combining, that basically means I'm talking about projection. Once I project all the point, I will be able to get that specific dimension. So I hope you have got an idea, but these are the steps that we basically follow in order to find out the projection. But at the end of the day, you are trying to find out with respect to any data points, you're trying to find out the best principal component line that can fit on this data such that it captures maximum variance. Now, like in this case, this can be, or in this case, this can be, right? So this can be my PC1, this can be my PC2. Why I'm saying this? Because maximum variance is captured. See, maximum variance is getting captured, right? So this was the idea behind principal component analysis. I hope you have understood the maths behind it. If not, I would suggest please revise it. I've written around 9 pages just to make you explain about principal component analysis. So yes, I will see you all in the next video. Thank you.